Hey everyone, and welcome back to this class, Modern Deep Learning in Python, Deep Learning in Python Part 2. In this lecture, we are going to discuss variable and adaptive learning rates. So far, we've looked at momentum as a modification to vanilla backpropagation that can greatly speed up training. And from my perspective, I find momentum to be the most impactful. If you compare the loss per iteration for standard gradient descent versus gradient descent with momentum, the difference is huge. At the same time, momentum is nice because you don't really have to play with the hyperparameters that much. Just go with 0.9 and it's probably fine. So momentum is often my go-to. At the same time, some of these adaptive learning rate techniques are very powerful. So let's have a look. The first thing we'll talk about is variable learning rates, or in other words, learning rates as a function of iteration or time. Sometimes people call this learning rate scheduling. They are very simple, but they give you a lot to play with. So the first one we're going to look at is called step decay. Essentially what we do is, periodically, say every 100 steps, we reduce the learning rate by a constant factor. So for example, we divide by 2, or halve it each time. If we plot it, you can see that it kind of looks like a staircase. The second method is called exponential decay. In this method, the learning rate follows an exponential curve. The third method is for the learning rate to decay proportionally to 1/t. You can control how fast or slow the learning rate decays by changing the proportionality constant. Notice how the drop-off is slower than exponential decay. So what do all of these have in common? Well, you can see that they all decrease the learning rate with time. Why would we want to do that? Well, generally speaking, when we initialize the weights of a neural network randomly, they're going to be very far from the optimal weights. So it's good to start with a large learning rate so that we can take bigger steps towards the goal. This is the motivation behind momentum as well. We want to pick up speed by accumulating past gradients because we know that if we are very far away from our goal, then those gradients should be large. But when we get close to the goal, the gradient is going to shrink. In fact, by definition, the minimum of a function necessitates a gradient of 0. That's how you solve for a minimum of a function in calculus, if you recall. You find the derivative and then you set it to 0, and then you solve for the parameter in question. So why might we want to slow down when we get close to the minimum? Well, when you're close to the minimum and you take too big of a step, you're going to overshoot. And so what ends up happening is you just end up bouncing back and forth. In fact, if your learning rate is too large, you'll just bounce right out of the valley, and your loss might actually increase. So in order to reduce all this bouncing around, we would like to take smaller steps. Here is another technique that people use which is related to these variable learning rate techniques. Sometimes researchers and machine learning practitioners will actually sit there and babysit the neural network training process. So they'll do a couple of epochs and see how it goes. If learning is happening too slowly, they might increase the learning rate. If learning is starting to even out, they might decrease the learning rate. But you have to be careful because you're not guaranteed to have a nice, monotonically decreasing curve. Sometimes you might get stuck in a relatively flat portion of the error surface, but this could just be temporary. And if you're patient enough, you might end up getting a steep drop. But at the same time, this is not guaranteed. As with most things in machine learning, the answer is that behavior is data dependent. Waiting longer is desirable if you have the resources, because then you get a full picture of the learning process. So manual learning rate scheduling is also an option for you to choose from. Now, also important to think about, what else do all these methods have in common? Well, all of these methods add new hyperparameters to your list of things to optimize. In fact, choosing between each of these methods can also be seen as a hyperparameter optimization. So in one way, Knowing about these techniques can help you, but from another perspective, it adds more work to your plate. The next couple techniques I want to talk about are what I like to call adaptive learning rate techniques, because they adapt to the training data that you've seen so far. The first one I want to discuss is called AdaGrad. The basic idea is this. We can't expect the dependence of the costs on each of the parameters to be the same. In other words, in one direction, the gradient might be really steep, but in another direction, the gradient might be really flat. So perhaps it may be beneficial to adapt the learning rate for each parameter individually based on how much it has changed in the past. So in AdaGrad, what we do is we introduce a variable called the cache. Each parameter of the neural network has its own cache. So for example, if you have one weight matrix of size 3 by 4, then you'll also have a cache matrix of size 3 by 4. And the same thing goes for your bias vectors. The idea behind the cache is that it's going to accumulate the squared gradients. Because we're squaring the gradients, the cache is always going to be positive. And because each parameter has its own cache, then if one parameter has had a lot of large gradients in the past, then its cache will be very large, and its effective learning rate will be very small, so it will change more slowly in the future. On the other hand, if a parameter has had a lot of small gradients in the past, then its cache will be small, so its effective learning rate will remain large, and it will have more opportunity to change in the future. One minor detail is that we usually add a small number epsilon to the denominator to avoid dividing by 0. Typically, this is set to 10 to the minus 8 or 10 to the minus 10. One important point to stress about AdaGrad is that everything we're doing is an element-wise operation. So each scalar parameter is effectively updated independently of the others, which makes sense. So you can look at the formulas we presented as scalar updates, which apply to all the parameters. Or you can think of one huge parameter vector that contains all the neural network parameters, and then each of the operations is an element-wise operation. This next technique builds on the fact that researchers observed that AdaGrad decreases the learning rate too aggressively. So the learning rate would approach 0 too quickly, when in fact there was still more learning to be done. This technique is called RMS-prop and was invented by Jeff Hinton and his team. So the way it works is this. The reason AdaGrad decreases the learning rate too quickly is because the cache is growing too fast. So in order to make the cache grow less fast, we actually decrease it each time we update it. We do this by taking a weighted average of the old cache and the new squared gradient. We call this weight the decay rate, and you can see that the two weights add up to 1. We'll be looking at this form again and again throughout the course, so don't worry about knowing all there is to know right now. Just know that we'll be taking part of the old cache and part of the new squared gradient and adding them together to get the new cache. Typical values for the decay rate are 0.99 or 0.999 or 0.9999 and so on. Again, the intuition for these choices will be discussed in later lectures. So by doing this, we say that we're making the cache leaky. And the reason it's leaking is because you can imagine that if we had 0 gradient for a long time, eventually the cache would shrink back down to 0 because it would be decreased by the decay rate on each round. One obstacle I realized some time after this course was originally released is that there is actually some ambiguity in the RMS-prop and AdaGrad algorithms. Specifically, I discovered this in the context of RMS-prop. So one thing that's not specified in the RMS-prop algorithm is the initial value of the cache. Now one might automatically just assume that 0 is a good value, and I did this as well. But this actually has a very strange effect. Let's suppose you choose a decay rate of 0.999. Then your initial update for the cache will be 0.001 times g squared. So you're taking 1/1000th of the square gradient. So disregarding epsilon for the time being, your effective learning rate actually becomes very large due to the fact that the denominator is very small. What you'd have to do is compensate by making your initial learning rate smaller than usual. One solution to this is to set the cache to 1 instead. By manipulating the RMS prop update a little bit, we can show that this gives us approximately what the update would be if we weren't doing RMS prop at all. Or in other words, the effective learning rate is approximately equal to the initial learning rate divided by 1. Now you might ask, well, which one is the correct way? And we can't really say because it was never specified. What I can tell you is that there are some very major packages that have implemented them both ways, so it's not as if one is more correct than the other. For example, in TensorFlow, the cache is initialized to 1. In Keras, the cache is initialized to 0. In fact, it's a great exercise to try and implement these adaptive learning rate techniques, then compare your implementation to these official implementations to check if your implementation is correct. If it is correct, then your loss per iteration should match what the library gives you. And so I've done this in the file rmsproptest.py in case you want to check it out.